Good morning, everybody. I hope you had a lovely Easter. If you did, I'm assuming staying in your houses and not doing an awful lot. We are going to carry on today doing more of the mechanics modules. I did have one email from Caitlin asking about the books. Sorry, I haven't emailed you back yet, Caitlin, but I'll answer it now instead. So we haven't got any of these textbooks at school. I assume we will buy them at some stage in the near future. It's up to you whether you buy them in the short term. You can get them from Hodder. Hodder is the textbook publisher, and the textbook is looks like this. And the one you want is A Level Further Mathematics Mechanics 4th edition. It has a lot more stuff in than what we need. We only need up to chapter 8. Basically, because MEI do a mechanics minor and a mechanics major. We're just doing the mechanics minor, which means it's about half as big as the mechanics major module. If you want the ISBN is down here somewhere. I need to move my drink. ISBN even is there. So if you do want to get hold of one, that's fine. However, I'm going to upload the pages as we need them and the answers as we need them, so hopefully that will be sufficient. If you want any more stuff, then please do let me know. But yeah, as I said, feel free to buy one if you want to. I assume that when we get back to school, whenever that may be, we will get hold of a load of copies of it, assuming that we can, and we'll carry on as normal. Anyway, we're going to carry on with this kinematics chapter today. We're going to start looking at variable acceleration. Remember last time we did something to do with constant acceleration. Specifically, we looked at the constant acceleration formulae. Remembering you have to call them that and not SUVAT, because Miss Hughes will murder you, possibly. So the constant acceleration formulae, because they only deal with, well, constant acceleration. So using them to do with things like when throwing the balls in the air, we know gravity's 9.8 or minus 9.8, depending on which way you decide to be the positive direction. It also works if you've got a car which is moving with a constant acceleration, for instance. Variable acceleration is a bit more fun, a bit more interesting, and there aren't said formulas for variable acceleration. The question will give you a formula at the start of the lesson. So at the start of the question, and you will have to manipulate that as you need to manipulate it. But it will normally only give you one formula, so it might give you a formula for displacement, and it might start asking you things about velocity, or it might ask you things about acceleration. And so what we need to do in this lesson is understand that there's a connection between displacement, velocity, and time. So how we're going to do that is by actually going back a step and going back to constant acceleration. These are two constant acceleration graphs. This is a graph of somebody moving away. It doesn't matter what this displacement is. It could be a person, could be a car, whatever you want this to be, whatever the time and displacement units you want it to be. It's not really important. But something is moved away from its starting position, then it's stopped for a while, and then it's moved away again. This is stuff that you've done at GCSE. And what I want you guys to think about is how these two graphs are linked together, and specifically, can you think about what the gradients represent? So if you can just pause the video for a moment and have a think about that, that would be quite useful. So hopefully looking at this one, you've had a think and said, okay, well, this person was displacement 0, now they're displacement 20, it's taken two whatevers. So if I asked you about what the speed was, hopefully you'd say, oh, well, the speed is going to be, they were at 0, now they're at 20, that's the distance they've travelled. Distance divided by time, the time is 2, so 20 divided by 2 is 10, so their speed is 10 whatever my jobbers. Let's say this is meters and say this is seconds, so 10 meters per second is the speed. And you'll notice over here I've got a velocity time graph which actually describes this one, so 10 meters per second for the first 2 seconds. This is a non-continuous graph. I've assumed that this person can start instantaneously and can stop instantaneously. They've stopped for a while and then they've carried on a bit further, and here they have travelled 30, they finish at 50, start at 20, they've travelled 30, in 1 second, so it's 30 meters per second is the velocity there, and I've wrote that up here. Hopefully you guys can say, okay, well you can just think about it, I was at 0, now I'm at 20, and it took me 2 seconds, or you can say, well the gradient of this thing would be 20 over 2, and the gradient for this one here, the change in y is 30 over the change in x, which is 1. So the gradient here describes the velocity. Not so obvious, but is true. The gradient here describes the acceleration. The gradient of this is 0, the gradient of this is 0, the gradient of this is 0. No acceleration happens at all in this because we're having this weird situation where something can instantaneously be a new speed, which obviously is rubbish, but for the purpose of the example it's useful. So for a distance time graph, the gradient is equal to the velocity. And for a velocity time graph, the gradient m, so let me write it out again, is equal to the acceleration, which you shouldn't necessarily believe me on that one because I've just used this trivial example where it's 0. So let's just show that that's actually true, not just from a graphical point of view, but also from the formulas that we've had and that you guys have seen. So one of the formulas I've showed you, one of the constant acceleration formulae, is s is equal to ut plus half at squared. Okay, what I want you guys to do is do some differentiation. T is a variable. Assume that u and a are constants. So t is the variable, t is the thing that can change. Can you work out what the differential is for this? And once you've done that, can you do it also a second time? I don't know if you've seen this in normal maths. Basically, if you have these 2's here, it means differentiate it again. Okay, so as in whatever you differentiated here, you differentiate it to here, then differentiate it again. Okay, have a quick go at those and see what we can figure out. Okay, so hopefully you notice when differentiating this first bit, assuming that u and a are constants, you don't have to assume they're constants, but when we differentiate with respect to the variable t, we're not considering anything else, so we can think of those as constants. So if I differentiate this with respect to t, this is t to the power 1, reduces by a power of 1, so this just becomes u. And if I differentiate this bit, I've got half a is the constant. I have to drop that power of 2 down to the front. That 2 comes down here. I then need to reduce the power by 1, so it just becomes a t. Or in other words, I've got u plus the half and the 2 cancel out, u plus at. Hopefully you've noticed that u plus at is one of the formulas we had the other day. I think it was the first one I wrote down. So if u plus at is equal to this differential, then that differential better be equal to phi. In other words, the gradient, because that's what this means, differentiating is just finding the gradient of something, the gradient of a displacement time graph is velocity. So this is another way of showing that this thing is true. If I differentiate this again, I'm differentiating this thing here. This is a constant, so it goes to nothing. And if I differentiate this, the power comes down, the power gets reduced, so this becomes t to the 0, and I'm just going to be left with a, acceleration. So I don't think this argument about the acceleration is particularly convincing. However, hopefully this is convincing. Remember what's happened here. If ds dt, yes, I'm differentiating it twice, but actually, really what I've done is I've taken what v was, what velocity is, and I've differentiated that to get a. So these two things here are actually the same as each other. And so hopefully that will be of some use today. Why would be of some use today? Well, we're looking at variable acceleration today. So we haven't got any of these formulas which we love are really useful, but we might get something else. So if I've got some other graph where it's displacement against time and it's a curvy graph, if I can find the equation of a tangent at a point, it can tell me stuff about it. So let's have a go at an example. Okay, so this is the example we're going to use. So a particle is moving in a straight line, its displacement is s, it's from a fixed point O. This is the equation for displacement at some given time. So if I wanted to find the displacement after time 4, I could just stick 4 in place of t and it will tell me what the displacement is. It says find expressions for the velocity and acceleration of the particle at time t. Sketch the graphs, which is quite a good question. Find the distance travelled between the two times and velocity is 0. Find the distance travelled in the interval 0 to t to 4. So what I'd like you guys to do is have a quick go at this. I'm going to do this as well. So if you pause your video, have a quick go at these questions. I will do each one of these obviously individually and take a small pause between each one so you can come back and check if you want to, or you can do all 4 in one go and then check it all afterwards. So either bit by bit or in one go. So pause the video now, have a quick go at some of this and then check back with the video. Okay, so let's have a quick go at part 1. So it says find expressions for velocity and acceleration of the particle at time t. The formula for displacement is this, and so if I'm going to want to find the velocity is the displacement differentiated once. If I differentiate this first term, I get 18. If I differentiate this second term, it's going to be 2 lots of this. That's going to be minus 42, and then drop the power by 1, plus 3 lots of this, so it's going to be 12, and then drop the power by 1. So that's an equation for the velocity, and for acceleration, that's going to be, well, you can write it either way. You can either write it as dv dt, or you can write it as the second differential of this. It's up to you how you do it. I'm going to write it as this for now. So this becomes nothing, this becomes negative 42, and this becomes 24t. Okay, so just before you start part 2, if you have already, do apologise. But if you haven't started part 2 yet, let me just give you some starting place. Save you going to a calculator and solving the cubic. So if I go for, let's see, minus 30, minus 20, minus 10, 0, 20, 10, let's go with that. Okay, so that's minus 30, let's go up a bit. Minus 20, minus 10, 0 and 10. Let's go across 1, 2, 3 and 4. So this is time, this is going to be displacement, and this cubic looks like, he says, quickly pointing out where the bits are, about there. So the minimum for this turning point is got a t value of 3, and the turning point here has, that's at half, that is. So it goes that, then through 1, then down here. My cubics are not good. Turning point's there, and it comes back up. Okay, that is a turning point, I promise. Not over there. So this is the turning point here at 3. This is the turning point here at half. Thinking about gradients, that might be quite useful for you. So have a go at the other 2 graphs if you haven't already, and check back with the video when you're done. Okay, so let's just have a look at these graphs. So this one has been drawn already, and if you weren't sure how to go about this, the best thing to do is stick it into your calculator. I'm going to tell you what the roots are, and I think it tells you what the local minimum and maximums are as well. This one you could stick into the calculator as well, so this is the velocity one. However, what you can do is you can use this graph, and this is something which they could do in exams. They could just give you a graph and say sketch this one. And the way you can do that is by saying, well, let's think about the displacement here. The displacement, so this thing is going away from the initial point, and then it starts coming back towards it again. If it's gone away and starts coming back towards it, that means that at some point it is stopped because it's changed direction. So it's stopped for a minute second. And it's stopped at the turning point. So it goes away, stops momentarily, comes back towards, goes away, stops momentarily, comes back towards. Because I know that it's stopped there momentarily, I can think about dragging those points down to here, and they must be the roots of my velocity time graph. It has a positive velocity to start with, because this would be a positive displacement. And then it starts having a negative velocity, negative velocity, negative velocity, negative velocity, negative velocity, negative velocity, negative velocity. And then as it turns around again, it starts having a positive velocity as it's coming back up here again. So thinking about which way that is, this is a positive gradient, positive gradient, positive gradient, and then it goes 0. Then it's a negative gradient all the way down here, and then a positive gradient as it goes up here. So I know what the turning point, I know what the turning points of those are, so I know what the roots are of this one. I know it comes in from this side to start with. I can look back at the equation and say, at 0 it's 18. You wouldn't necessarily get that if you were just given this, you would just have to, roughly guess. So it's 18, jumps down through there. It does go down to about -20, but that's not necessary unless it particularly asks, and then it shoots back up there. It would be important to note what these are if you were to ask about it, and it would be important to note this bit. I wouldn't necessarily suggest you start working out the vertexes. That was 18. And for the last one, the acceleration, well, this can be done similarly using the graph, or it can be just, it's a linear graph, -42 plus 24t. I haven't put anything on here. Let's put some stuff on. Let's say that's 25 and 50. -25, -50. Okay, so here the velocity graph, the velocity is changing, the velocity is changing, the velocity is changing, the velocity is changing, and at this particular moment it stops changing for a minute second you can think of. Or you can say the velocity goes from decreasing to increasing. And because it goes from decreasing to increasing, that must mean that the acceleration is momentarily 0. So let's just mark that on. So the acceleration, that really should be at 2 apparently. No, it's not at 2, is it? It's just off to the side. Yes, that's right. So it's around about here, whatever that would be. You can stick it into your equation and find out. The y-intercept's -42, so we get this sort of thing going on. That'd be -42. Okay, so there'll be some common misconceptions with this. The most common misconception people have with this sort of thing is that because the velocity here goes through 0, they feel like there's some sort of, the acceleration must have been 0 at some point, but it's not that at all. The acceleration is only 0 when the velocity actually the velocity curve stops increasing or decreasing for an instantaneous moment, and that's only as you come here. It stops increasing or decreasing for that moment there. A way of thinking of this possibly would be if you had 2 rugby players and there was a collision. The first one was running at the second one. Let's say the person with the ball is moving very fast. The person without the ball isn't moving at all. The person, let's say this is for the person carrying the ball, they hit the person who's tackling them. They immediately start to slow down. let's say that the tackler is doing a particularly good job and then starts pushing them backwards, so their velocity becomes, the ball carrier has a negative velocity now. But after, whatever this is, after 1.78 seconds or so, the person carrying the ball actually gets their studs back in the grass and starts pushing backwards again, or maybe their friend has just caught up and started pushing them. So you can think about it from that perspective, but they are decelerating all this time, even though their velocity becomes negative, and then they can start accelerating again out of the tackle. So let's leave that one for now. If there's any issues with that, please get back to me on that one. And there's just part 3 and part 4 to do, so I'll quickly just do those two. So this question, part 3, is quite a good one. It asks for the total distance travelled, remembering that distance travelled is different to displacement. Distance travelled doesn't have any concept of direction. So this is something which we got from, which I told you from the graphs, but you would want to solve this in the first instance to find out the two different times when the velocity is 0. The velocity 0 at t equals half and t equals 3. Looking back at our graph, we could work out what the displacement is here by sticking half into it. We could work out the displacement here by sticking 3 into this formula here. And the distance travelled would just be the difference between those two displacements. If you stick t equals a half into the formula, 18 times a half minus 21 times a half squared plus 4 times a half cubed, and you bang that all into your calculator, I'm hoping you get 4 1/4, so that's at t equals a half, and at t equals 3, if you bang 3 in, you should get negative 27. So that's the displacement at the first point, that's the displacement at the second point. Therefore, distance travelled we've gone from 4 1/4 to minus 27. So the difference between those, the positive distance between those, is going to be 31 1/4. Which doesn't sound right. No, it's right. Okay, so I'm just going to quick get number 4 as well. If you haven't done number 4 yet, then please do so now. Okay, so what we want now is the distance travelled in the interval 0 to 4. So it's very useful to come back to the graph and just think about what things you need. So the first bit is up to here. That's for when the displacement is going in the same direction. And that amount there is 4 1/4. And we know that's 4 1/4 because we just worked it out a minute. The displacement at t equals a half is 4 1/4. So that distance is 4 1/4. For this section here, from half to 3, we just worked out a second ago, it's 31 1/4. We know the displacement here is minus 27. So what we really just need to know is what the displacement here is, because then we can work out what this distance is. So we need to work out what the displacement is at time equals 4. So at time equals 4, if you stick that all into your formula, I can promise you get negative 8. So therefore, for that section, therefore, so let's call this, and it's a useful thing to do in your exam, let's call this C or something like that. Saying this is A, this is section B, this is section C. Therefore, C, in terms of distance travelled, is going to be minus 27 to minus 8. So that's going to be 17, 19, isn't it? That's going to be 19 altogether, minus 8 minus 27. So what you need to do now is just say, well, if they're the 3 different distances, that one, that one, that one. And if I add them all together, I'll get the total distance. It's really important that in this bit of it, you don't just write therefore total distance equals the answer. It's really important that you write down this, because there will be a method mark for noticing that to get the total distance you have to add up these things together and not just do something with the displacements, but actually adding your your distances of each leg. When you add those together, you get 54.5. So it's really important that you get this method mark for making sure that you're doing that, just in case you cock up and write 77 billion or something stupid there. Okay, so I think we might just leave it there for today. We can do some other bits and bobs. Probably not too unsurprisingly, if we've been doing some differentiation today, we could go the other way with doing some integration. But I think for now, let's just do some stuff involving differentiation. So if I just set you some exercises, and then tomorrow we'll do the integration stuff. So if you can just do exercise 1.3, questions 6, 9 and 12, I'll attach the whole exercise and the answers to the class charts, to class charts, and I'll also stick it on the VLE. Tomorrow when we do the integration stuff, I'll give you some more questions to do, because I won't be doing such a long video tomorrow for that. Hope you're all keeping well, and I'll speak to you again tomorrow. Bye bye.